Welcome to the Chapter 10, Section 2 podcast. This is on rotational speed, and the main idea about this section is tangential speed depends on rotational speed and the distance from the axis of rotation, and we're going to see that in mathematical form in a few minutes. So let's go back to a turntable. And so we have a turntable that rotates about its axis, and we have a ladybug sitting on the turntable, and at its edge it's revolving around the same axis. So the question is, which part of the turntable moves faster? The outer part, where the ladybug is, or the inside part near the orange? So this depends on whether we're talking about linear speed or rotational speed. So linear speed is the distance traveled per unit time. And the point on the outer edge of the turntable travels a greater distance in one rotation than a point near the center. So we say the linear speed is greater on the outer edge of a rotating object than it is closer to the axis. And we call this something moving across in a circular line. We call that speed the tangential speed, because the direction of the motion is always tangential to the circle. So you can think of it this way: if you have a let's put a pen here. If we have two lines, you can see if we take this, there's one path, and here's another path. And if we take this line and lay the line out, if you look at this first line, is roughly only that long, and the second line is about that long. So you can see that in a in the same amount of time, the outer path traveled a greater distance in the same amount of time. And we can think of it as, I like to think of the linear speed as, if we took the path and laid it out in a line, which one would travel the further distance in the same amount of time. Now, rotational speed is also called angular speed, and this is the number of rotations per unit of time. So all the parts of the turntable rotate in the same about the axis in the same amount of time. So all parts have the same rate of rotation. So each of those, let's go back to this. We'll go back to the turntable in a moment. Or same number of rotations per unit of time, and we often express this as revolutions per minute. And you can see there are two dials usually on your car. One is your velocity, your speed, not velocity, but your speed in miles per hour, and then the second dial tells you your RPMs per RPMs of your car, which is how really a measure of how fast your car is working, not how fast the car is going, but how fast your engine is moving. So let's look at this again. All parts of the turntable rotate at the same rotational speed. So a point further from the center travels a longer path in the same amount of time. You can see this is a short line, this is a much longer line, and they're doing that in the same amount of time. So a ladybug sitting twice as far from the center moves twice as fast in linear speed or tangential speed. So the tangential speed is directly related to the rotational speed and the distance from the axis of rotation. So here's that proportional to. So we can see we're starting to build a formula here, and we write this like this: V is the tangential speed, omega, which is this character right here, is the rotational speed, and r is the radius. So the faster the rate of rotation, the bigger the omega, and the further from the axis, which is the radius, the bigger r. So you can see this as if the object rotates quicker and you're further away from the center of the object rotating, the greater your tangential speed. So, and in the center of a rotating platform like this right there, that child sitting right there, they're not, they don't have a rotational speed, they just rotate in one place, or rotate, the axis is internal to them. Once you move away from the center, then your tangential speed increases while your rotational speed stays the same. And this reminds me, as a child, we used to play on these merry-go-rounds. You don't see them too much anymore, but we used to play on these merry-go-rounds, and you always found that if you sat in the center of the merry-go-round, you weren't thrown off the merry-go-round. You rotated in one place. So, and this is like old Calvin and Hobbes cartoon, which kind of sums up what I'm trying to explain right here. So, here's the thing. At an amusement park, you and a friend sit on a large rotating disc. You sit at the edge and have a rotational speed of 4 RPM and a linear speed of 6 meters per second. Your friend sits halfway to the center. What is her rotational speed? What is her linear speed? Well, your rotational speed is going to be the same. It's also going to be 4 RPM. But her linear speed is 3 meters per second, which is half your linear speed, because she is halfway to the center. So her radius is half that. So if her radius is half, then her linear speed is going to be half of your linear speed. So how do the wheels of a train stay on the track? And you're probably saying, well, what does this have to do with rotational speed and linear speed? Well, the rims on a train are tapered, and you'll see a better look at it. Actually, you can see it a little bit right here. This is tapered ever so slightly, and it's tapered here too. So let's try to set this up and understand this. A cup, if you lay it on its side in a cup that's tapered, it's going to travel in a circle as you roll it on a table, because the wider part of the cup right here is going to travel a greater distance per revolution than the inside part of the cup. So it rolls in a circle, because the wide part of the cup travels faster than the narrow part in linear speed. So we put a pair of these on a track and we roll them along that track. The cups will always remain on the track, and I'll do this in class to show you. And the center will they'll always start to center themselves as they roll off the center. And the reason why is when the cup gets too close to the left, the wider part of the left cup will the wider part of the cup will actually rotate more and steer it back towards the center of the track. So as it then if it overshoots back to the right, then it the wider part of the cup starts to travel on that side again, and the wheels will center themselves again. So this is essentially the same thing that happens on a railroad track, and you can see when you see a curve, you'll see why you need the tapered wheels to force the train back into the center of the track. And once again, the distance along the outer part of the track is longer than the distance along the inner part. So when a wheel follows a curve, it's going to travel to the outside of the track. So the outer wheels will travel faster than the inner wheels, and that's fine, because as it goes around the curve, the fatter part of the wheel is going to be on the outside of the track, which is going to be larger. And and they're always going to rotate together because they're fastened like the cups are. So, and here it is looking at it as you see it goes occurring. You can see the narrow part here is traveling less, so this side is going to move faster, and then it's going to correct it back and move the wheel to the opposite side. So the wheel is going to move, the train is going to move that way, because this side is going to move faster. So let's do a train. Think. Train wheels ride on a pair of tracks. For straight line motion, both tracks are the same length. But which track is longer for a curve? The one on the outside or the one on the inside of the curve? And the outer track is always longer. Because it's basically, you can think of the two tracks as circles, and the outside track is going to have greater circumference. And once again, the outside track is where the wheel is going to ride on the fat part, and it's going to travel further. So what is the relationship among tangential speed, rotational speed, and radial distance? Tangential speed depends on the rotational speed and the distance from the axis of rotation.